his lecture or talk already, what I plan to do is also to give maybe a bit more details of the complete calculations or of the overall scope of things which he is doing and which I'm doing with him in the last maybe 2 years. So first I will talk a bit about the calculation very briefly. Then I will introduce some details of how one defines the calculus in this case. In the third part, I will give, in this particular case, some details of the differential geometry of this, so to say, non-commutative manifold. And then I will discuss what can one do with the components. So the motivation. Motivation to do something which could be described as non-commutative geometry and non-commutative field theory. It's not only because similar structures were found in string theory, I think. The motivation is more basic. And so if you want to, with some, well, seriously to combine quantum mechanics with general relativity, you soon realize that for some or the other reason, the combination of the two implies the lower limit on coordinates, which would then somehow tell you that you should have something like uncertainty relation between the coordinates. So not the coordinate momentum uncertainty relation, but just between the coordinates. Of course, such a possibility was many years ago welcomed because such a lower limit would give you ultraviolet regulated quantum field theory. There are many possibilities to realize, so to say, or to quantize gravities in some sense. And the one which I will talk about is the third Rockley possibility, described as non-commutative geometry. What you can hardly see is the mentioning of Einstein's name, so basically because it's the year of physics related to 1905. So, but I think this non-commutative geometry is done really in the spirit of Einstein. Not only because it's developing geometry and then relating it to physics, but also because what you basically do is try to combine or to explore the consistency of various theories, which Einstein did for maybe promoted mainly as a method of investigation, and to try to somehow find a coherent way to combine them. Or what I wanted to show here is that when you generalize, in this case, or there is a trial to generalize general relativity to non-commutative gravity, you can expect always singularities. If you take the limit, for example, from quantum mechanics to classical, you have to take the singular limit of hy tends to 0. And also, what is known, if you try to find the limit from non-commutative to commutative theory, you also have the singular behavior. So in principle, there are all kinds of singularities and you have to find a way to define them or to deal with them or understand them. So which are the elements of generalization in this specific case? One is the possibility to generalize the notion of differential or differential structure that is of continuous structure, more or less, to non-commutative geometry or to define the differentials and derivations in the algebra. But the other thing is also that you would wish, and there we see that in fact this basically is a quantization, not only that we are dealing with any non-commutative generalizations, but a sort of you want to also retain symplectic structure and to be able to talk about momenta as well as coordinates. So you have sort of to have both, and that is. So now I start to define things a bit more precisely. So what I will talk about, or what one can call non-commutative space, is some algebra. And usually it's generated by a set of operators which we call coordinates. Of course, these coordinates do not commute, so in principle they satisfy some set of relations which could be, but not necessarily written in terms of commutators. So the commutator of the two coordinates can depend on coordinates, and this is what we would call the most general case. If we have the constant commutators, that is the most investigated structure, the canonical structure. So with constant non-commutativity. But as I said, if we are talking about general relativity, in principle, there is no reason to put the commutators constant, especially if you think of coordinate transformations. It is possible to define differential structures of the algebra, for example, vector fields, as derivations, that means mappings which are linear and obey Leibniz. Well, Leibniz is not, maybe not necessary, or we heard or we will hear about the theories where derivatives have some more general or deformed properties, so deformed Leibniz. So here we assume that the ordinary Leibniz rule is always and the other structures are one forms. For one form or P forms in general. So you can define also on algebra one forms, which then map vectors to algebra, so mathematically. And the important thing for physics or that you can multiply from the left and from the right side. So you ask for disclosure in a sense. And then you can generalize. You can generalize the exterior multiplication and also the differential. So the differential on the forms one defines also for a Leibniz rule and the usual d squared equals 0. Of course, this doesn't give you uniquely still the structure, although you can show that it exists. The framework which is used here is the generalization of the moving frame formalism. So you start with the frame, with a moving frame. So it is a set of one forms, and obviously it can, or in the classical case or in commutative case, it gives you also the metric. So it's a local like frame. So either you start with the one forms, or you start with vector fields, with tangent vectors of each. So what basically we are doing is, I think, quite clearly, the version of John Mador, which is minimal. And I think it's therefore it's at least worth investigating until the final consequences. In which sense it is minimal? First, the assumption is that all derivations are inner. So that all derivations have a form of the commutator with some elements which are in the algebra, and these elements are momenta. So it is a very, although the commutator obeys Leibniz rule and this derivation, it is not at all clear that you, so it is a big restriction. In quantum mechanics, the derivations are out there. The other assumption is that momenta can generate the whole algebra as well as the coordinates. That is the other non-trivial assumption. And this is sort of gives you the idea what is the dimension of this manifold. Because if you have n coordinates and then momenta, you can think that this, or not a manifold, this non-commutative space corresponds to a n-dimensional, or should have a commutative limit which will be an n-dimensional manifold. And the third assumption is that the center of the algebra is trivial. Therefore, so there are no, only numbers commute with the whole algebra. This simplifies the calculations a lot, and so in this sense gives further restrictions. So what I can see that the advantages is, as I said, you have some notion of a dimension which is not at all trivial, not in the algebra. Starting with the frame, you can at least at some elementary or obvious level discuss the commutative limit, since you have the frame which is defined also in usual gravity. And the further property is that the structure is very constrained. Well, that is nice, but and therefore maybe it's important to see what's there. But what I see from doing examples that it might be that the structure is too constrained. So we would like to see whether this all this framework has or contains some physically relevant spaces or physically relevant examples. It's worked out quite a lot, and the whole formalism I will show just some of the results maybe which. So how to define a differential? The differential is defined in terms of frame like this, and then we have a number of constraints. For example, the frame has to commute with all elements, with whole algebra, with all elements of the algebra. Here is a very important and strong constraint that, in fact, momenta always obey a quadratic relation. So these numbers, in the notation P, F, and K are numbers. So this is maybe unexpectedly strong constraint that we deal just the quadratic algebra when we are talking about the momenta. And of course, analyzing this algebra, one has to assume something about the associativity, and well, the trivial thing is to assume that algebra is associative, or the most straightforward, which gives you so you always have to check Jacobi identities, whether they give something else or not. The example, which is simple but important, is that of a flat space. So really, when coordinates commute into a constant, you can define the calculus, and then the momenta are proportional to the coordinates, more or less. And when you work it out in more detail, first you see that the frame is the D of coordinates, so you see more or less immediately that it is counterpart of the Minkowski space in this non-commutative way.
Can you see? I'm missing why the fact that H commutes with one forms is a constraint. Can I see?
Why is that a constraint?
You are imposing it.
No, you conclude that from this definition of differential, well, all this it's non-trivial. I mean, you would need a bit more, like 3 lines to prove it, so it's not immediate problem, obvious. But, would you like to see it proved or what?
No, maybe later, maybe later.
Yes,
So it's
you
the
can-
right-hand side of the definition of
It's the
differential.
definition that then you conclude that theta commutes with all elements. So I don't know at the moment whether it's... Maybe it's not trivial, but it's not difficult also. And then you have to impose the differential respect. Yes. And also from this, and then in this you have also, or you use also the fact that momenta generate the whole algebra. So that in order to come to this relation, which is so that's the structure of the differential calculus. So this is for what I think the simplest example. I mean, one could investigate 4-dimensional examples, but it's also maybe the easiest thing to see what it gives in 2 dimensions. In 2 dimensions. And in a particular case, when you assume that the frame or everything depends only on one coordinate, so that d over dt or not, in this case, is a killing vector, to speak gravitationally. So this would be more or less the most general answer for the frame. And then we can now analyze a bit how to define a differential, or when we define a differential as we did, it gives in terms of coordinates, what is the calculus. And you easily see that starting with this sort of a frame, you obtain these formulae so these rules, so to say, of differential calculus, which I wrote so that only dt times t is not trivial, so that only the time does not commute with the differential. Then you find out that the commutator of t and x is a constant, it has to be a constant, and moreover that one forms in principle do not anti-commute, so that you have this would be an interesting typically not, as coordinates do not commute, obviously one forms also do not anti-commute. So basically this set of rules you have for also without imposing this assumption that the derivatives are inner. So you have some set of, you have a differential calculus and it's not too constrained. In principle, for any function f, you could define differentials, but if you now impose this assumption of inner derivatives, then you see, or of the quadratic algebra, then you see that the structure is almost completely fixed. And of course of Jacobi identities, that is what it's. So basically you obtain the equation for the function f. I mean, this is a bit in details, but so you have the equation, which has only 3 solutions. It's not difficult equation. It's the first order equation, partial, ordinary equation, and you have more or less, not more or less, but exactly 3 solutions. One is a flat space or 2-dimensional Minkowski space. Then you have the solution of this type is something like anti-de Sitter or de Sitter space, depending on the initial signature, or Lobachevsky plane, maybe not in a typical, but after a transformation, exponential transformation of coordinates, you can get this Lobachevsky plane. And the third solution, which maybe is a new one, is this, which we call a found it also in the non-commutative scope. But the third one, as it is, well, not at all completely clear how to define the curvature on the non-commutative space. So this is important from this aspect that at least the classical analog does not have a constant curvature. Why we call it the fuzzy torus? Because it's really, if you do big rotation, it really is a metric of a torus with the, but not the general one with the hole which is singular. So it's so these are a bit details. So this is the curvature.
So you get three solutions without specifying the non-commutative algebra?
What?
You haven't specified the non-commutative algebra. You just make the assumptions that the roots are inner and all these things.
No, non-commutative algebra in terms it's fully specified even at this point. I mean, you immediately get that the T and X are constant. I mean, when you analyze a bit these constraints, you get the differential of T and X have to be zero. And since everything depends just on X, more or less immediately you get a constant. But that doesn't fix you the frame or the metric. F of X is basically the metric hidden. So, but then when you impose this quadratic momentum algebra, so momenta are very important as well. That fixes you the metric almost completely, or metric in the sense of its commutative limit, or classical limit. That fixes the function then completely. And then you don't have any freedom anymore. You can just have three possibilities. I mean, I didn't try to, it's not a difficult calculation of any difference. So I wanted now to say a bit about the differential geometry. So this was the calculus. There are two basic quantities which are important to define connection and metric and torsion in this framework. One is this matrix pi, P, which in fact can be defined as antisymmetrization. So it is a projector which defines how the one forms multiply, or defines a wedge product. And obviously, it can be more general than we have in the usual case. So it's not only antisymmetrization. So in the usual case, it's just antisymmetrization. But in this case, it's something which is more general. In the frame formalism, this matrix is constant. So it's and the other thing is how to define the change of order in the tensor product. It's called flip. So it's another mapping which defines more or less the change of indices, and it can be used to define what symmetrization of indices is. In non-commutative cases, this is 1 plus sigma, or identity plus sigma. And then there is this whole formalism which allows you to define the covariant derivative, the connection, and so on. And I will not go into details. I mean, it's big formalism more or less. But what is important that we need, what is absolutely necessary is to define this P and S in this case. So that in principle it's not really easy to find these two objects, the projector and in complete generality. So I'm writing this non-perturbatively because when I will come back and sort of define these objects in the limit non-commutability goes to 0. Right? They also have to satisfy some constraints of the type that P is a projector and it is Hermitian. So these are very elementary requirements. And also flip is, well, done double, it has to be identity or maybe not. This is just a hermiticity and this is a source of orthogonality too, so that symmetrization is orthogonal to anti-symmetrization. And this set of constraints is difficult to solve in general. Even in this easy case, which we did two-dimensional case, we didn't succeed to solve these constraints in full generality. Therefore, the tactics was to define a sort of, as I said, commutative or semi-classical limit. So to assume that the projector has the main part which corresponds to the flat space or which corresponds to a commutative limit plus a correction, which is proportional to some small parameter k bar, which is analogous of h bar. That's more or less, and the same thing for the flip, for the matrix, and for everything else. And then you try to solve these constraints order by order. This can be done in this case. It is it's more or less algebraic, as because all these coefficients turn out to be constants. So we can solve for, so I'm showing you this, just the solution. So Q defines the projector, and you can see immediately what the projector is more generally. And the classical connection defines this, the flip. So you can also solve for that and find the correction for the matrix. So besides the Minkowskian part, you find a certain off-diagonal element which looks superficially not Hermitian, but in fact, if you really think what the non-commutative definition of reality or hermiticity and symmetry is, it's real and symmetric. And of course, then you can find the correction of the curvature in the first order as well. So you find this correction of surface. What we did is, try to find the second order correction in K bar, and it's possible to do it. But what happened is that you can find all, but when you find connection, it is not metric compatible. So you can put the torsion-free condition and everything, reality, hermiticity, and everything, but the connection is not compatible with it. So I come to the conclusion. So what, or how I see this, these results, I don't know. So in 2 dimensions, we discussed this special case of dependency only on one coordinate. And there we found that there are not many possibilities. The structure is very rigid. You cannot get much of it, although you have one or more, or 3 at least possibilities and an interesting example, but it doesn't give you any flexibility. If you try to do more general, so to try the dependence on both coordinates, that is quite difficult, because you do not know a priori what is the commutator of the coordinates, that is what you would like to get. But then if you don't know that, you don't know how to work with them. So maybe you can do semi-classical limit. But assuming that everything has a general dependence on 2 non-commuting operators, you cannot do much exactly, unless you know the solution. So, of course, we did, or John does for many years, these 4-dimensional examples. And I am also now convinced that 4 or higher dimensions give you much more freedom. So in principle, you can get many more maybe relevant examples. Some something you can learn from 2 dimensions. So there is, sometimes you get a structure which is a tensor product. So sometimes the solutions reduce to these 2-dimensional, sometimes not anyway. But still from the examples which we did, or which I did in some detail, it is not clear. So you can work out many examples. You can work out both the calculus and the differential geometry, but it is really unclear whether preferred or correct, so to say, classical limit can be obtained. So that's the main point. Whether you can start from any classical configuration, for example, Friedman, Robertson, Walker, that is what we did. And when you try to do everything, so you assume Kevin ansatz, which is Friedman, Robertson, Walker, you work it out in the momentum space, and when you go to the coordinate space, for example, you get something which breaks the spherical symmetry. You get some axial symmetric matrix. Well, for me it's okay, but maybe it's not really. So maybe you would, and since it's not clear at each point whether you can do something better, still we don't know whether this structure is too restrictive or not. So I think it's worth really pushing to the final consequences. Of course, you can do generalizations. I mean, easily in this formalism you can have higher dimensions. So maybe that is worth, in principle, doing. Or you can change the formalism by adding outer derivations, and in that case, I would say that almost certainly you can get a scope where you could discuss something like arbitrary non-commutative spaces.
Does somebody have some question, comment?
How can you define that 2 coordinates don't commute? Because I don't see why coordinates should commute always.
Maybe they don't. I mean, how do you know that they commute? Maybe that's the very secret of the nature.
Why did you not find the standard non-commutative term?
Why?
So you have found it, or?
Probably the differential, yes.
But you could have found it.
And so it's not really a general torus, it's a singular torus.